with the talk devoted to random measures as a model for coalescence structure in stochastic flows. Please.
Okay, thank you for introduction. I will share my screen now, and here is the slides of my lecture. So I will talk today about point processes that associated with a system of points with interactions. And today we will start from some examples that came from physics, and we will see later how we can describe such a system with point processes. So let's start the lecture. So the first example that comes from quantum physics is systems of particles such as bosons and fermions. So here I will give such a brief introduction. So we will consider a system of indistinguishable particles. So this means that we cannot say which is which. So, and when we consider it with a time, they somehow interact, but they're mainly what we will study the distribution of particles at some point of a time. So like if we have some picture, and when we stop time, we will have some distribution of a particle in the space. What are the way to describe the quantum system? So in quantum physics, they use so-called wave function that depends on n arguments, which are parameters of a particle. So it is a space position, for example, etc. So we have n particles. And for us, it is most interesting what we can do with this wave function. So we can say about the probability to observe specific quantum state. So I write that this quantum state is n-dimensional vector in space of parameters of a particle. And this probability is equal to square of modulus of wave function. And here, what I said before, since we consider particles that are indistinguishable, so we cannot say which is which, what is the first and what is their second particle. So this means that probability to observe quantum state does not depend on the permutation of parameters of these particles. So I just I consider any permutation of particles, and the probability will be the same. So we do not say that we can say that one particle, for example, A, B, and then they move, And for example, here we have BA. So we do not know what is what after a time. So this is assumption that we have. And after this assumption, we have two cases for wave function, which leads to two types of particles. So if wave function is symmetric, we have one class of particles, so-called boson. And if the wave function is anti-symmetric, this means that we have a deal with another type, so-called fermions. And later in our lectures, I want to show that such systems can be described with a point process of different types also, and we will see that this simple assumption. So we just assume that wave function can be or symmetric or antisymmetric, and we will see that this leads to different behavior of a system. So we will see this, for example, for bosons. We will see that they can for example, two particles can be in one place, but for fermions they cannot be at one place, two or more particles. So this is main difference between these point processes that we will later consider. Okay, so this is one example and one motivation from quantum physics, and we will see later how we will get described. Okay, so for the next example is a system of Brownian particles on a line that starts from every point of the line and move independently up to the meeting. And after meeting, we will consider a case when they occur less and move later as one particle. And another case of a system with Brownian particles is a system with annihilation. So if we consider some number of particles that starts from different points, and they also move independently, but when they meet together, they annihilate, so they disappear. And here, the question that I will be interested in during these lectures is to investigate the property of position of the particles at fixed time t0. So I fixed time t0, and the question is how I can investigate the position of these particles here, and also in this case. So here later we will see that we will have another class of point process that can describe such a system of particles on the line, and this point process is different from the previous example that I described about quantum physics. So here once more about assumption for Brownian flow with coalescence. So I just recall here. So that each trajectory in this picture is a trajectory of Brownian motion, this one property, and they move independently before meeting. So each two particles here moves independently and coalesce after meeting. And such object arise like a mathematical model for processes of turbulence. For example, if we consider a flow with some such one, so we can consider here this like a particle, and so we assume that they can coalesce after meetings. So if they have for example, if they're together, so close enough, they will coalesce and form one such weir. So also another process is process of calculation, and also for aggregation processes we can see such pictures. Okay, so as I said, I will try to investigate such random systems with interaction using point processes. But here in this case of coalescing Brownian particles, let's answer for a question. So why do they meet? So, and here we consider this. We consider a simple case. We consider just two Brownian particles that start from some points here, and so I did not write here. Sorry. Let us assume B1 from 0 is equal to some U1, B2 of 0 is equal U2, U1, U2. So we have two independent Brownian motions up to their meeting. So the question is, do they meet? Because maybe we do not have such a good picture like I draw here. I draw here just a finite number of particles at time moment t0. So we need to be sure that they indeed meet. And here, not very difficult to understand that if I consider a difference between two particles, it is for now for independent, it is also a Brownian motion, but with variance 2. And from this follows that the probability that they meet is equal to probability that a Brownian motion hits 0, this one. And we know that this probability is equal to 1. So this means that any two trajectory in this picture will meet one another sooner or later. But moreover, it is known that there is such a property that for every positive time t, for any interval AB, for example, we will find here a finite number of particles. Here the property, it is a little bit hard to prove, but this is what is known. So, and now we can see that yes, indeed, we can investigate this difficult system that starts from uncountably many the particles, but we can investigate it using a theory of point processes because we have here a finite number of points at any bounded subset. So this is a brief introduction and for why we need to know something about point processes. And here I will give a short introduction for a point processes itself. So what is a point process? How we will understand it? So a point process is a random collection of at most countably many points. And it can be a point of any nature, but here for simplicity we can imagine like n-dimensional Euclidean space. This is enough. So for example, if I just put on the interval 0, 1 n independent uniformly distributed points here. So we will have some random collection of points here. So this is one way how we can understand a random collection of points. So this is just some points, but the better idea to consider not the points, but the measure that we can associate to these points. So if I have a point from some space, I can say that this point defines a delta measure in space of counting measures. So this is idea that we will not consider some system of points, but we will consider measures that describe these points. So from the previous example, like that we consider if we have 4 points, we took into the correspondence the measure of sum of 4 delta measures in these points. And it turns out that it is much more better to work with measures and not with this just the collection of points in a space. And now let me give you a precise definition for point processes. And as I said, we will consider space Rd, it is enough, or R, so for simplicity. And this is the strict definition of a point process. So by n with sign less infinity, I will denote the space of all measures mu on Rd such that for every parallel subset, the value of measure mu is natural number. So we understand that mu is a countable measure. So it counts some points. So this is, for example, okay, and using these finite measures with values in natural numbers and zeros, I form the space of all measures that can be written as a countable sum of measures from this one. So one of the most common example of such such measure is the following. So if we consider a sequence of points in Rd, here k can be as natural or infinity, it doesn't matter. And if we will consider a sum of delta measures in these points, we will get a measure from this space. Yes, indeed. So we can count the value of mu of b. This is just the sum of indicators that xn belongs to subset p. So we just count the number of points that belongs to subset p. So this is a very simple example of such a measure. Okay, and since we want to introduce a random measure, we need to understand what is a measurable structure of the space of random measures here. So we want to define a random measure like a random element in this space. So, and for this, we need to know what is the sigma field that we will consider on the space of measures n here. So we will consider a sigma field that is generated by the collection of such form. So here just you need to understand that this is the smallest sigma field on the space of measures, such that such mapping from so this is mapping from the space n to and infinity. Yes, that such mapping is measurable for all subset B of measurable subsets from the space. And now we can define a point process like a random element eta on this measurable space. So we have a space of measures with sigma field and measurable mapping from probability space to this space of measure is a random is a point process by the definition. So let us consider a simple example, and the simple example is, of course, the most simple measure that we can have here. This is just a delta measure at some point x, but now x is a random element. So I start with such example, but is this a point process by the definition that I gave? And yes, indeed, what we need to check that such event, so this is now we need to see that this belongs to sigma field that we have on our probability space. And yes, indeed, this is true because we just need to write all the cases that we have, that eta of b can have 3 values, and these events are in sigma field F because x is a random element here. Okay, so this is a simple example, and for as exercise, I want to propose for you to prove that such a sum of delta measures at points x1 and so on. Xm is also a random element, and moreover, it is interesting to find the probability that value of some set B is equal to k. So it's, and here x's are independent random elements with some known distribution. So this is like exercise. Okay, so now when we defined a point process, now we need to understand how we can analyze it. So we should have some properties or of such object, and as analog of mean or variance of a random variable, here we will have so-called intensity measure of a point process. So, and intensity measure of a point process is defined as expectation of value of point process from some subset B. And indeed, from the basic property of expectation here, we can see that lambda indeed measure. So you just need to check all properties of measure, and it is simple. And as exercise, I want to propose you to find the intensity measure of the point process that we considered here. So it's not hard. And it turns out that this intensity measure is very useful, and the property of this measure in the following proposition. This is so-called Campbell's formula, and it says how we can calculate the first moment or expectation of the integral of some function with respect to point process. So let us consider eta, that this is a point process on Rd with intensity measured lambda, and u is a function from the space Rd to R, and then their integral of such form is a random variable, so that this is like one of the statement. And moreover, expectation of integral just equal to integral of this function with respect to intensity measure. So here we can have a picture. So let this will be my function u, and measure or random point process eta is here. So integral here is just following sum of these values. So, and this turns out that sum of the values of function and this random points is equal to integral with respect to intensity measure. And for proof, I will give basic steps. So this statement is simple for function u, which is equal to indicator of some subset B, and indeed we can write the integral. This integral is nothing else that the value of measure eta from the set B, and this is just the definition of intensity measure of a point process, and we can rewrite it in terms of integral because u is indicator function. Now, using linearity of expectation, this property we can get for the function u of the following form as sum of weighted indicators of subset bk and here just as I said, we just use linearity of expectation and the previous step. And step 3 I did not write in details, but here we need to consider, for example, non-negative function u and approximate it by a step by a sequence of step functions. And if we have the equality for step function, we just need to go to the limit and we will get the statements of this proposition, so-called Campbell formula. Now I want to illustrate all of this by very simple example. So this is so-called Poisson point process, and this is maybe the most known and the most investigated point process, and we can define it as follows. So at first we take some locally finite measure lambda on R, for example, and we will define a Poisson process with intensity measure lambda as a point process eta with the following two properties. So the first property is that for every subset B here, I'm sorry, from the space for measurable subsets of R, we have that eta of B is a Poisson random variable with parameter lambda of B. So that means that this probability is equal to such a value. So this is just a definition of a Poisson random variable. And another important assumption that if I take any number of disjoint sets B1 and so on Bm, so here also, which are measurable, then the random variables of eta of B1 and so on eta of Bm are independent. So if I have non-intersecting sets B1, B2, the number of points in these subsets are independent. Note here that we say that in this definition we defined a point process with intensity measure. So indeed we need to note that this measure lambda is an intensity measure from the previous definition. So indeed we can see that the expectation of eta of B, we know that this is a Poisson random variable, and we know its parameter lambda of B. So we know that expectation is equal to lambda of B. So indeed, in this definition, lambda is intensity measure of this process. And the question is, does this point process exist? And yes, it is. And we can construct it as a sum of random numbers of delta measures. Let me be more precise. I will consider some probability measure on, I'm sorry, we can consider here R. So, and I consider independent random elements or random variables in R with this distribution Q. And now let me take a random variable kappa, which is a random variable with Poisson distribution with parameter gamma. So this is some number. And also I need to assume that this kappa is independent of sequence of x's. And then if we define random measure like sum of random number of summands, here the most important that actually if we do not know the number of points, yes, so this is a random value which is Poisson, and here we have independent the delta measures of independent random variables, and it turns out that this is a Poisson process with intensity measure gamma multiplied by this probability measure Q. How to prove this? So actually you need to find the probability of eta of B, for example, and then also to check independence. But here, for example, for one, for such probability, you just need to consider all cases of let me use number n is equal to 1 to infinity, and here probability, sorry, eta of b is equal to some k equal to some 1 to, of course, probability to some number n delta x k, and the event that k is equal to this n capital. So we know that they are independent. We use I'm sorry, this is, let me use, this is kappa, and this k, let me use here n k, and they are independent, so we know how to write them. This is a probability. I'm sorry, here also I forgot about summation. N is equal from 0 to infinity. And n is equal from 0 to infinity. And actually this, the first probability here is the probability of exercise 1. So I just leave for participants to check this. So this is not hard. We know the distribution of this sum. It is non-random sum now, and we know the value because k is kappa is a Poisson distributed random variable. So this is not hard. Okay, now I want to consider the example of a system of Brownian motion with of Brownian particles with coalescence, and here we will define the following measure. So let us define for the first that x from ut is a family of Brownian particles that starts from each point of the real line. So on the picture, as I showed it before, I have from each point, I have a Brownian trajectory. So this is x from ut. Okay, but if we consider two particles, so they behave like this. So this is two representatives of the flow. But if they start from every point of the line, this means that we have such a very complicated picture here. This, so, and so on. And I fix some time t here. So let me take this time t. And I will define a point processes as follows. I will count the number of points that came from all line to some subset B. So this is my subset B. And I count the number of points in this subset B, like this. So here is equal to 2. So this is the definition, and now I want to show that we want to find the intensity measure of this measure of this point process. And to do this, we will start from not from the arbitrary subset here, but from the interval from 0 to u. And to do this, we need to talk about so-called dual flow. And to understand this idea, we will start from the Gaussian random walk on Z. So this is the picture, and let me describe it. So here I consider a family of random walks that starts from points 0, 2, 4, and so on. So from even natural numbers. And they move independently, right or left, with probability 1/2. And if they meet, they coalesce together. So this is a discrete analog of the flow of Brownian flow with coalescence. And moreover, we will start these random walks not only from their initial 0 time, but from any point of the time. So here's the main idea that I start this random box from each point time here also. And I get such a system, and the dual flow we form in reverse time. And we construct it as follows. We start from here, let be some point time t. We start from the each now even points here, and we move in backward direction as follows. So if I have here the value in the black flow in this that direction, I move forward in this one, and so and so forth. So at each time I have exactly one way to move in backward that direction here. And if we construct such a picture, let us note some interesting property. So if I want to count the number of points that came from to the interval from 0 to u here in my forward flow, so I have 2 points here, and let us consider that in the dual flow, in red flow, that starts from the points in the interval 0u. So I have this starting point, I consider them. And from this, and this also, from these points, I have 3 points here, exactly 3. Okay? So this is the main observation, and we can define such a structure for continuous case. So here in the black, I have a flow of Brownian motion with coalescence. And so I have such a picture. And again, I consider points that are in these intervals. And this means that if I start the backward, also called dual flow, in backward direction from this interval, I will have +1 number of points in original here. And the property of this dual flow is the same of the forward flow. This is also a flow of Brownian particles with a coalescence. So the main idea of such construction, so here just a picture and intuition, but this dual flow can be constructed in details, but I want to use here just one idea that if I consider now the slightly different point measure that is defined as follows. So now I count not the point that came to the interval 0u, but I consider point that starts from 0u now, and they go to here to some time t, and I count them. So this is from the duality property. Okay, so now I will consider this new version of T, and the main property that we have one more point in this process if I compare it with initial eta that I considered. Okay, and now I want to find the intensity measure of this point process mu. So I count the number of points that starts from set B. And to do this, we will do as follows. So since I start from interval 0u, I will consider the uniform partition. As follows. So I have points u0, which is 0, and so on, un. And I will consider the particles that starts only from these points. So only this one. Only these particles. And I will define the following moments of the time, tau k. And this is the first meeting time of the trajectory, for example, for tau first. This is the first meeting time when it meets x from u0. So this is tau first. Then for tau k, this is the first meeting time of Brownian motion that starts from uk, and the time when it meets the particles with these lower starting points of this subset. So here we do not have, so this is bigger than t here. And now we can count the number of points using these moments of time. Indeed, so just a moment. So we can count the number of particles that from 0 to u at time t. So I consider only this one. So I count that one for which tau n is greater than t. And this means that I count this particle. And I will write here limit, because we will get this answer when we will increase number of sub-intervals. And now we need to find the expectation of such sum. And to find the expectation of such sum, so here k, of such sum, we need to find the probability that time of meeting is greater than t. And know that here, actually, each tau k has the same probability. So we have equal probability here, because they have the same distribution. And we can write it in terms of some Wiener process. So this the idea that I considered before, that we can consider time of meeting as between two Brownian motion as if I consider, so this b of t, w of t, let me write it. So in my notation, I'm sorry, w of t is equal, for example, x from u k t minus x from u k minus 1 t. Okay, so, and we know that these are Brownian motions. So let me so this is a Wiener process. So for this, I can find this probability using just standard Wiener process. And I need to be sure that it is not less than u over n for each moments of time from s to t. And this can be easily calculated because we know the distribution of maximum of Wiener process. So this is just the such integral of the density of standard Wiener process at time t. And what is the main feature that we need to note here, that this is equivalent to such number as n tends to infinity, because we need the limit as n tends to infinity here. And after substituting these probabilities to this sum, we will see that the expectation of their number of points. So I came back here to initial point process here, of Brownian flow with coalescence. And from this, we can see that the intensity measure of the point process of this, I'm sorry, I didn't, of this point process is equal to Lebesgue measure multiplied by some constant that depends on time t. And this is natural, because for small time t we have a bigger number of points here, and it turns out that this is proportional to the square root of time t. So here 1 over square root of t. So for here we know that approximately we will have here such number of particles that have such intensity measure. So this is very important properties, but this property of the point process that we consider today, this is intensity measure of a point process. And this intensity measure describes only behavior of one point, for example, yes? Because we just know how to find the expectation of integral. But if we need to find the properties like the second moments, or if we want to consider multiple integrals, we need to know a little bit more about point processes. And this is what we will do on the next lecture. We will discuss how we can characterize and how we can calculate higher moments of a point processes, and we will see that we can define some functions that characterize higher moments of a point process, and using this we will see how we can characterize the point processes from which I started today's lecture about bosons and fermions. And we will see that we will have some classes of points processes which characterize a different behavior of particles in the space. So this is all for today's lecture, and thank you for your attention.
Thank you very much. Maybe there are some questions or comments, please. Okay, if there are no any questions, let's wait for next lecture. Maybe after the end of the lectures, we will have some questions. And please pay attention that next lecture will be next Thursday at 9 in the morning at Kyiv time. Thanks everybody, and see you next week. Bye.
Thank you, Katya, for interesting lecture. Have a good day.
Thank you.
Thank you. Bye.
Thank you.